Hello everyone, good afternoon. So I'm sorry I'm 1 minute late. This week will be on algebra. So we will deal with quite some algebraic manipulations of polynomials and equations. So in middle school, you will see that frequently algebra problems tend to just test you on your familiarity with equations and polynomials. Rarely you will see some functions at all, if any. But certain topics, favorite, test, just kind of sources, like quadratic equations and the Vieta formula. And today we'll see good examples. It's very important for you to do some basic reading of the materials on the subjects, not just to just do problems without understanding the theoretical just things behind the scene. So that would be kind of very inefficient or unproductive way of studying algebra for competition math. You do need to read the books. Okay, so let's see our first problem. If you watch the video, this is actually one of the earliest AOPS mini. This is number 4, which means that this was during the very first year when Richard at the AOPS tried to produce this 100 strong series. This was during the first year, so unfortunately, none of the minis, the 9 minis from the first season, had any official solutions. I do have some by my own, but I still have not found time to produce every just early mini solutions. But number 4, there is a solutions document. So this problem, you see that you are provided with 2 equations, and there are 3 variables, x and y. The interesting thing is that on the left-hand side of the equation, there's certain kind of symmetry here, right? X plus y over 1 over y, then y plus 1 over z. When you see something like this, your gut feeling or your intuition should be, this probably involves some cyclic symmetry. What we mean by that is that if you have x plus y over 1 over y and y plus 1 over z, then naturally it would be nice if you have something like a z plus 1 over x. That's just a kind of intuition. On the other hand, what you are being asked to do is something like x, y, z. This by itself also exhibit cyclic symmetry. Cyclic symmetry meaning that when you have 3 variables, say you have 3 variables, if you replace x with y, y replaced by z, and z replaced by x, essentially the same set of conditions and the same problem statement here. Okay, so that means that you should think about the property of such cyclic symmetry. Also, we recognize that with 2 equations and 3 variables, in general, we don't have any just unique solutions for x, y, z. Meaning that if you fix 2 variables, the other one, the third one, can freely change. That's in general the case. However, that doesn't mean that even x, y, z as a whole may have infinitely many solutions because you only have two variables that can be fixed, and the third one will be just changed according to the first two. There's no unique solution for XYZ for sure, but that doesn't mean that XYZ, this particular thing, cannot have a fixed value. Well, that means that XYZ as a whole, they can all change, but they will change in certain way that there's still a constraint among the three. And that could result in a fixed value or constant value for XYZ. Those are the general observations for this type of problem, because in many cases, a particular problem doesn't require you to have some intuition into the nature or the particular nature of the specific problem. Okay, so let's take a look at XYZ. That means that we somehow need to multiply all the three together, right? That's just what it is. On the other hand, we don't see that in the original two equations. But because the two equations eventually can be simplified, or we just get rid of the fractional portion, at least making it more explicit. So the first one would be really xy plus 1 equal to 2. And the second one would be y times z plus 1 over z. That's simply, we add them up, right? However, you do observe that there's something interesting, because we want to get something close to what we want. That's the x, y, z time together. So at this point, we are really being tested on how to cleverly manipulate those algebraic expressions. What shall we do? Well, because we need to get a term that has x, y, z all multiplied together, but in those two expressions we don't have any. Ignoring the denominator part, if we just look at the numerator, we do have two that each has two of them. The first one has xy and the second one has yz, so probably want to multiply them together in some way. That's the only way you can generate some term which contains x, y, z all multiplied together. So why don't we just do that? So, and also, it's very helpful you recognize that on the right hand of the two equations, you have a pair of reciprocals. And what that means is that when you multiply them together, you get a very nice number 1. Okay, let's just give it a try to see what happens when we do this. Now, if we multiply the left-hand side of the two equations together, you will get the bottom, the denominator would be yz, and the top would become x y squared z, because xy times yz, you get 2 y's, then you get xy, you get a yz, and plus 1. The right hand side nicely becomes 1. Okay, now you see that we really want to get rid of the bottom, and now this becomes y times z, right? And then we can cancel out this. So this really becomes xyz y squared plus xy plus 1 equals to 0. Okay, so this is something close to what we want, but it has one extra y in the product. So naturally, we would want to get rid of that. And the way to do that is obviously divide both sides by this actual term y, and then we get something like this. And because right hand side is now 0, nicely, nothing will happen. And we do know, by the way, y cannot be 0 in the first place. Otherwise, this equation would have no meaning at all. So we know we can safely divide both sides by y. So the right hand side remain to be 0. And then we can nicely see that this thing is gone. So what we have now is xyz plus x plus y over 1, y 1 over y, I'm sorry, x plus 1 over y equals to 0. Now we have isolated or produced something that is exactly what we want to know. Okay? But the process is that you don't do this randomly. And there's no hope that you can magically just produce this. You do this, follow a procedure that kind of just follow a very well-educated guess. You are going through this direction under the belief that what you want to do and how to get there. So although this is a kind of just trial and error, but it's not just randomly walk in the dark. It's something really guided by our intuition. And now you see the fruit. We have this one. So if we know this guy, now we will know the result. And do we know this guy? Yes, we do. This is exactly the condition that was provided to us, right? X plus 1 over y equals to 2. So now we know immediately xyz equals to -2. Just because they just move this to the right hand side. And now you see that how we get xyz. So in theory, what we learn from this problem is that although we don't seem to have enough information to give a complete solution of x, y, and z, no unique solution, but we should believe, because this is a kind of just a made-up problem, we should believe that there must be a unique answer to x, y, z. Otherwise, this problem would be an incorrect problem. That is just kind of just a cheating fact, because we know this is a valid problem. So there must be a way to manipulate the two algebraic equations to somehow arrive at least x, y, z. So the problem really becomes, how should we manipulate the two expressions to get here? And we first simplify the two kind of annoying fractional cases to get something that look more promising to get x, y, z. What we did is first by just getting those two expressions, now we see we want to multiply them together, and that's just an educated guess, hoping that it will lead us to something closer to the target. And now we see something like this. And the rest is just kind of even with better guidance, because we know we want to get x, y, z. That is a good post for us to search for direction. Okay, hopefully you just don't memorize, and there's no way to memorize a trick like this. You do learn how to perform educated guess, do all the logical reasoning, but there's no guarantee, even when you try your best, you can solve the problem. Quite sometimes you will succeed, but there are other times that can lead you to nowhere. Then just back off, try something else. Okay? That's where problem becomes more challenging. Okay, the next problem. Okay, this time the problem becomes a little bit different, because now we see that there's a slight change. The first problem and the second problem looks very similar, except this term now is 1, previously is 1/2. Remember when we have 1/2, when we do the multiplication, 2 and 1/2 cancel out each other, they're reciprocal, we get 1. Now apparently that's the difference. And turns out this difference is quite significant. So, but if another thing is that when you are provided with a problem that looks similar to something that you have already solved, try to consider the two together to see what is the difference and whether such difference introduce something that can get us into the insight into the nature of the problem. So if in the first problem, if this is 1/2, we get a unique value of x, y, z. If this now is 1, what does that mean? Meaning that the nature of x, y, z multiplied together probably will not be exactly the same as the previous one. And the way this problem is asked, then is there only one possible value of x, y, z? So by merely looking at this question, you should feel that the answer is probably not, because it would be very kind of unusual if you change the numerical a little bit, x, y, z remains a constant. That can happen, but more likely than not, it probably won't. But your challenge is to prove, if that's the case, prove there's no only one possible value. So that means that x, y, z can change. But a good way to start with some problem like this is that based on what you just did previously for the similar problem. So we will do exactly as what we did earlier. So essentially, we multiply the left-hand side together. Let's just put them into a fractional form first, okay? So the first equation says that xy plus 1 over y equals to 2. And the second one, yz plus 1 over z equals to 1, okay? So now, if we multiply them together, yz equals to xz plus xy plus yz plus 1 equals to 2, right? Okay, so get rid of this, we get yz plus xy plus yz plus 1 equals to 2yz. So these two introduce one actual yz that is really a troublemaker. So we manipulate this a little bit. So put everything on the right hand side to be so yz got cancelled 1. So this is a minus yz plus 1 equals to 0. Okay, this is nothing but we just subtracting the 2yz from the other hand. Remember last time this guy completely disappeared, but now it's there. But we still want to get xyz, evaluate the xyz. So now we decide to divide both sides to be 0, to divide both sides by y. So we continue the same process, divide both sides by y. This guy becomes x, this guy becomes minus z, and we get y over 1 over y. The right hand side remains 0. Now we have isolated this. And now see that actual 1 on the, because now this is a 2, the real impact is that now we have one actual copy of negative z. Otherwise, it would be exactly the same as last time, right? And from last time, we do know that x plus y over 1 is something already given, which is 2, right here. Okay, so now we see that what happened is that we just have to deal with that actual negative z plus 2 equals to 0, right? And this is exactly the troublemaker, but it really helps us to answer the question, because the problem is not ask you to get the value. The problem is there only one possible value of x, y, z? Clearly now we know x, y, z, last time it just equals to negative 2, but now it's z minus 2. So it doesn't matter what you get, x, y, z, when you multiply them together, it's always equal to z minus 2. However, do we have a unique solution of z? If we do have a unique solution of z, then this will be unique. But the answer is apparently no. Hell no, because as we said, we have two equations but three variables. In general, there's no unique solution at all. We can always give two, just change one variable, and the other two will be just say z can take any value. When z take any value, x and y, now you have two equations. Now you uniquely solve x, y. In other words, both x, y can be, you have certain solutions like this. You have, if you change z, if z is fixed at certain value, now you get a solution for x, y. So therefore, x, y as a pair can be considered as a solution in terms of a function, some functions of z. Whenever z changes, x, y, they do have solutions, but that solution will correspondingly change along with z. So clearly, this thing will not have a unique value, because you can always freely change z, right? You can give z any value. Therefore, the answer is easily, there's no only one possible value of x, y, z. It can be whatever value you want to get. Okay? So this problem introduced some troublemaker, but clearly the question also gets changed. And it's quite easy to answer this question if we really can understand our last problem. This problem just adds a little bit twist. Okay? So it's not that surprising. Now, next problem. Once again, we have something. This time, the right-hand side, instead of 2 and 1/2, we get both 1 on the right-hand side. And you immediately guess that this should be something really close to a cyclic identity, and that is exactly what we are asked to. Then must we also have z plus 1 over x equal to 1. If we do, then the 3 are actually, exactly cyclically symmetrical, right? X plus 1 over y, y plus 1 over z, and z plus 1 over x. So our intuition should tell us this probably should be true. Because in that way, you have a complete set of symmetric relationship. It's 1. It's 1. And if this one is also true, then we will have completely symmetry. So our guess is that this is really true. And intuition tells us probably should. However, we don't have just a easily immediately available insight. So what shall we do? Well, you think about it, what we are being asked for. To evaluate an expression that is kind of cyclically symmetrical to the other two. But it also means that in this relationship between x and z, there's no y there. So we want to evaluate something really that only involves x and z. And this relationship must be somehow derived from the first two, right? That gives you the idea of how to attack it, meaning that in order to go from here to here, what happened? The y must be gone. It needs to be canceled out. That's the only way to get something, let's just say, a function, a two-variable function of x and z. There's no y. Y cannot remain. So that gives us some insight that we want to manipulate those two expressions so that y can get cancelled. And because of the particular structure, it's quite obvious. You think about what's the most efficient way to do that. Well, you have 1 over y, and you have a y. Then apparently you want to isolate those two, then multiply them together, right? They are reciprocals. 1 over y and the y. If you multiply them, then boom, it's gone. So this leads us to take an intuitive direction. We don't know whether this will work, but at least it's the right direction as appears. So we want to isolate those two. So y 1 over y becomes 1 minus x. And the y becomes 1 minus 1 over z. Right? We isolate those two. And the next step is obviously multiply them together so that we get 1 y cancelled. So 1 equals to, in this case, it's 1 plus those two multiplied together, x over z, then minus x minus 1 over z. Well, this is something that we want and we believe should be close to what we have here. Because now we can cancel this y. That's really nice. And as we said, we don't like fractions, so we can further, now we move everything to the left-hand side because we are used to that, put the right-hand side at 0. Now apparently we want to multiply both sides with z. So when we do that, remember now this is on the left-hand side, we get x minus xz, 1 minus xz, then minus 1 equals to 0. Remember, all this happens just we multiply this guy by z. But now, see that this is not something close to this. But what is this guy anyway? This is really something we have 1 over x. You can think about the connection between those two in two ways. First, we may think this is as x and xz plus 1, right, equals to 1. And this is really xz plus 1 equals to x. So whatever this is, we can evaluate whether this is true. So this is apparently xz minus x plus 1. And now you see that this is actually exactly this one. Right? Magic! But this is not surprising because as this is a valid problem, it must be something like this. At the end, as long as you are under the right direction, it will lead you to the destination. Because that's the only way this problem to be a good problem. Because we want a relationship between x and z, and we have already achieved this by canceling the y, so there must be some direct relationship between this one, what we have. That's the only thing we can get a pure expression involving both x and z without y, and this is what we want. So there must be some connection between them, and from here we get here and we get here. Then it's because this step and this step, they are all equivalent, meaning that they can lead to either each other in both directions. So we really just want to evaluate the relationship between this one and this one, and apparently this is exactly the same. So another approach is that you can think about this way. There's 1 over x, so probably you want to divide both ends by x. That's still the same thing. Just doing from the other direction, but essentially the same algebraic relationship that controls the result. So if we do that, the second approach would be, say, divide both sides by x. Why? Because we see that there's 1 over x. So if we divide both sides by x, this would become 1 minus z minus 1 over x equals to 0. And once again, this term with the negative sign is exactly what we have here. So either way, we prove those identities are actually exactly the same. They are equivalent identity. They can lead to each other. Therefore, because of this, we check that this is indeed right. This is indeed always true. That answers our original question. Then must we also have this identity? The answer is yes. And we prove it by following our guided intuition, educated guess. So once again, you have to develop this kind of logical reasoning capability which help you, but does not guarantee you are on the right track. It's just we kind of take an educated guess. This could be the direction that hopefully lead us to the destination. And every time so far, we have succeeded. Okay? Important, you do not just become a robot, just try to memorize this trick, that trick, but you do need to develop this kind of reasoning capability. What is the intuition here? How that can guide us toward a promising direction. Okay? Alrighty. This problem. Well, everybody should be familiar with this kind of problem, right? It's just a repeated theme. And this is actually called continued fraction. And it's a big or huge topic for understanding rational numbers and real numbers. Actually, real numbers can be defined as a continued fraction, but that's a very advanced topic we don't want to touch at all. But for Mathcounts, this kind of middle school competition, a problem of this nature is simply you observe the particular pattern, so then you get the equation, then solve the equation. That's it. This is very mechanical because the trick is overall idea is all similar. Those kinds of patterns could be like this continued fraction or nested radicals and so on. But all comes from the same thing. There's a big assumption here. We assume there's a value of this because we don't even understand what this is exactly. Look, what is exact this? We cannot even finish this, right? So the only way to define this is through a concept called limit, a sequence. But we don't actually even know what this means, okay? Because this expression is not finished, meaning that this is not actually a well-defined expression, unless you have some really advanced knowledge. But in that sense, this is not a rigorous problem because we don't even know what do we mean by writing this. What is this? You cannot finish it. This has to be defined through a series, and that goes to infinite many terms, and we define that as a limit. But for now, we just assume this is a valid value. There's a value associated with this expression, and that is key. So that this guy, whatever this is, equals to x. Okay, this whatever, just this continued fraction. But the structure is clearly this, because right beneath the first 6 in the bottom of this fraction, it's itself, right? Because once again, this is 1 plus 6 over 1 plus 6 over, it never ends. This is the infinity. So this x really is 1 plus 6 over x equals to x. That's how you get an equation for any expression of this nature. Kind of just standard trick and very kind of mechanical. You recognize a repeated pattern, assume this expression has a value, and then you get an equation. But that was a big assumption, and to understand it, you really need to study advanced math, which there's no place in middle school math competition. So all you need is that you understand the value we want to get comes from this equation, and we want to solve x. So this is actually a quadratic equation in disguise in terms of this. Apparently we can get rid of the bottom of the fraction, so multiplying both sides by x, and that came under the assumption that x cannot be 0. But this actually, from this mere expression, this seems to be the case, right? Everything is a positive. How can this be 0? This result must be something positive. But once again, that's a big assumption. Even so, this looks like the case, because every time we have the positive fraction, how can this be anything like a 0 or negative? But what if, say, what if this is a negative, can it make sense? It may. It's just that by observing this alone, we cannot jump to the conclusion that this thing can never be negative. Fortunately, in middle school math competition, it's not that rigorous. Okay? So in theory, this can be negative. But as we see, we solve this equation. So this would be times both sides by x. This would be x plus 6 equals to x squared. So the quadratic is x squared minus 6 minus x minus 6, right? And we can, it must be very basic skill. You do know how to do polynomial factorization for simple things like this. You don't have to invoke the quadratic formula, because in this case it can be easy. It's x minus 3, x plus 2 equal to 0. Why? You do the crossing, right? 1, 1, you test it, because we want to generate a negative 1 coefficient for x, the linear term. So this is apparently negative 3 and 2. And this, by the way, is called cross factorization, because you just get educated guess to put a negative 6, decompose it into 2 numbers, and they add up to the coefficient of the linear term. And apparently with negative 6, we can, if you are really good at number sense, you get negative 3 and positive 2, then they add up to negative 1, which is exactly what we have here. So with that, we can easily factorize this into this. So now you have 2 solutions. X equal to 3, x2 equals to negative 2 from rows 2. Okay, now you see that indeed, in theory, this term can be either 3 or negative 2. In theory, there's nothing wrong if we just say this is negative 2. It will still make this recursive just expression work. For example, if this is indeed negative 2, so this is negative 2, 6 divided by negative 2 would be negative 3, then plus 1 becomes negative 2 again. That's exactly the meaning of solving this equation. We have 2 solutions which both must satisfy the original one. That's why if you plug in negative 2, this will still make sense. But the educated argument is that this can never be negative because every step of the way you are doing positive things, right? So the answer is this is a 3. But just remember, it has a big kind of doubt. There's a cloud there why this cannot be negative. Fortunately, either in AMC or Mathcounts, you either have a multiple choice or you have one correct answer. Nobody will try to put a negative 2 there, right? If you do, you really need to do something better, okay? You just cannot put the negative 2 into the solution if this is a Mathcount. You always, of course, you want to educate the guess this is positive, all right? So that really helps. Okay, the next problem is how to prove the AMGM inequality in the special case in the 2 case. And this is really nothing just special. It's a very standard, well-known trick. Everybody should memorize this. This came from the fact that, you have binomial square, okay? Because you really want to prove, usually we don't like to write inequality in this direction, do you? I personally prefer always write inequality in this direction because that's how we write numbers from smaller one to bigger one. It goes up to the right. So I prefer write inequality in this direction, not the other direction. It's a personal taste, but I just don't like it. So let me rewrite the inequality in this way. So we want to show square root of the product of xb is less than this. Okay. So first of all, we need to understand a and b are both positive. Therefore, this is equivalent to if we take both sides by square. So this is equivalent to a plus b squared. It's very important when you solve inequalities, you do not lose some solution, or you just, because if this is just one way, you may not get it back, okay? When you do square root thing, that can perfectly happen. But fortunately, because we are already told both a and b are positive, so if you do have this one, right? Because let's just say without a, b being both positive, if we start from here, can we get to this point? No, because a plus b can be negative. Because this is just what it can get to if we know a times b is positive, not a and b are individually positive. What this can give us is to get the square root smaller or equal to the absolute value of this. This is equivalent. This is always true because we know this is always non-negative. So this, if this guy is smaller than this guy, the square roots are also following this inequality direction. But without knowing a and b are both positive, we cannot remove the absolute value. Because a and b could be both negative, and in that case, the direction of the inequality will change the direction if that's the case. So it's very important when you work with inequality to be mindful that when you do a manipulation, you are not exchange the nature of the original relationship, because otherwise you are working on a smaller set of solutions. Because if this one way, this is not the same thing as the original one. This is a weaker condition than the original one because it's one direction. From here you can get to here, but from here you cannot go back to there. That would be a disaster. Very, very important to understand this kind of thing, okay? But now, fortunately, because we were already told both A and B are positive, we know this is equivalent, okay? And what do we need to do? Well, this is just the rest is simple, right? Let's do a little bit manipulation, times both sides by 4. So you want to prove this. This is nothing but a binomial. Now you see what to do. This is simply saying that minus 2ab, but this is nothing but a minus b squared, and which is perfectly legit. And again, every step of the way, you have to have, it's bidirectional, meaning that you're truly doing equivalencies. Because the reason for that is that we just show this is true. 0 is definitely equal to or less than this one, because this is a square, it's never negative. So this is always true. But every step of the way should be go back. From here you can get to here, from here you can get to here, and finally from here you can get to what we want for the original AMGM equality. Even this is very simple, you do need to know how to manipulate inequality a little bit. And the AMGM inequality in general, if you have n terms, it's still legit to say the geometrical average is never bigger than the arithmetic average. Arithmetic average is a plus b plus c plus d divided by the total number, and the geometric average, you say if you have multiple terms, you take n square root of the product of row 3. So AMGM inequality is saying that the average of rows is never, the geometric average is never bigger than the arithmetic average. Or in other words, arithmetic average is always bigger than or equal to the geometric average. And usually when this happens, all numbers involve the positive integers, because it doesn't make sense if one of them is negative and the total number is an even number, then you will have a disaster. You cannot properly define the negative. So assuming all those numbers are positive, how do we generally prove the AMGM equality? Actually, that's a kind of difficult problem. There are many ways to prove that. And one of the, I just want to mention this as an enrichment thing, okay? There's a very beautiful proof by Cauchy, one of the greatest mathematicians, French mathematician in history. He has an incredibly clever method by using merely very basic algebra. He used induction on that. And the way he used induction is he used a forward-backward dual direction of induction to prove the AMGM equality. It's absolutely just a genius method. So try to go to AMGM's Wikipedia page to see there are many proofs there. Search for Cauchy's induction proof. It's absolutely just amazing. Okay, so let's see next problem. We have 10 minutes left. Okay, here comes the big deal when we talk about this. Okay, both things are, I'm always a big advocate you should not memorize anything. But still, it doesn't hurt if there are some tricks that are so common and so kind of frequently tested, then you should really just kind of know that just even during your sleep. So that means that there are certain things that if you know the trick, you will know the solution right away or very quickly. If you never learn the trick, then it will be very difficult. Okay? And here we go. This is a standard trick called Vieta's formula. Okay? So the next couple of problems are all just that. So the problem is that both roots of the quadratic equation of this one, x squared minus 63x plus an unknown constant k, are prime numbers. So this is good. The roots, first of all, what is the problem? We have a quadratic equation, but this quadratic is indeterminate in the sense that the constant term is unknown in the first. It's a k, which we need to work out. But in any case, say k equal to 1, k equal to 2, every time k is fixed, you have just a normal quadratic equation. Then you will get two roots, right? Sometimes you will have to get complex roots if the determined, the quadratic does not have real number solutions. But the point is that for any value k, you will have a pair of roots, and hopefully they are both real roots. On the other hand, this problem is just stated in the roof. Now, we don't know k yet. We know certain properties with those two roots. That is that both roots are not just integers, they're prime numbers. Both roots of this equation are prime numbers. So what is the number of possible value of k? So that's a big constraint. At this point, this may appear an extremely hard problem if you don't know the trick. Indeed, if I do not know the trick, this will be a horrible problem or extremely difficult. I have no idea because I have to now get the general formula. So x squared minus 63x plus k, right? Equals to 0. I have to use the negative b, that's 63 plus minus b squared minus 4ac, that's 63 squared minus 4k over 2. So that is the quadratic formula giving me the two solutions. And now the constraint is that both those solutions are prime numbers, and what could k be? It does not help at all if I get this. What the heck is that? I have no idea how to guess a k to make both prime. Right? So if I don't know the trick for this problem, use a very hardcore, straightforward approach to get both solutions, write them down in a form like this, it doesn't help at all. It actually makes the problem even worse. I have no idea what k should be. In order to make it, first of all, you need to make this radical disappear. You need to get a kind of perfect square inside the radical. And after that, you still need to verify overall values of prime numbers. For God's sake, that's just impossible to do. So what can we do? Well, fortunately, any competition math students at this stage for this problem should know the trick. And it's so famous, it's called Vieta formula. And Vieta actually, historically, he was the first guy to actually introduce the fundamental concept of algebra using symbols A, B, C, X, Y, Z to represent unknowns in math problems. That gave us equations. So you should really know this name, Vieta. Okay? I believe he was an Italian. So what is the Vieta formula? Well, Vieta formula in general for a higher degree polynomial, that's a more general term, but for quadratic equation is something like this. We know the quadratic equation is ax squared plus bx plus c equal to 0, right? The Vieta formula says that because we know this quadratic equation always has two solutions. It's just sometimes they are not real numbers, could be complex numbers, but if you haven't learned what complex numbers, just take face value of this thing. But most of the time, for you guys, always, either you say they don't have a solution, meaning no real solution, or they will have a real solution. But regardless of what happened here, there's a pair of relationship x1 plus x2 equals to negative b over a, and x1 times x2 equals to C over A. This is the relationship between the two roots of any quadratic equation. The sum of the two roots is always equal to this term, negative b over a, and the product of those two is always c over a. And while not a rigorous proof, we can imagine why this works. The very reason we say this quadratic equation always has two roots is because we have a theorem called the fundamental theorem of algebra. Just by the name, you know how important this theorem is. The fundamental theorem of algebra states that for any such polynomial equation, it always has number of roots. The number equals to the degree of the polynomial. In this case, is the second degree. So you have two roots. Also, the roots do not have to be distinct, or they don't have to be unique. You can have the same root multiple times, and that can be better understood on a complex plane, meaning the two-dimensional complex plane. But that's too advanced for you guys. What you can intuitively understand this theorem is that you can always decompose this or factorize this polynomial into something like x minus x1 times x minus x2 equal to 0. Apparently, you can get rid of leading coefficient a by dividing that. A cannot be 0, otherwise this becomes a linear equation. So because this is a quadratic equation, assume that a is not 0, so we can divide both sides by a, and you get a quadratic equation with the leading coefficient of the highest degree term just by 1. So therefore, after doing that, you can factorize the polynomial into this way. Because we know it has two solutions, x1 and x2, so it must be, the equation must be equivalent to this. X minus x1 times x minus x2 equal to 0, because that's the same equation gives you two such solutions. One is x1, one is x2. The challenge is to prove this, that this must be true. If we know there are two solutions, x1 and x2, then this polynomial must be always exactly like this. That's for advanced math, but you don't have to understand or worry about that for now. But the intuition is that's why we call this the intuitive understanding. If that's the case, we can always transform the original polynomial into something like this, because this is the one that will give you exactly the two polynomials of the roots. If that's the case, we can expand this. What is this? It's x squared minus x1 plus x2 times x plus x1 times x2 equal to 0, right? This is nothing but just expanding this, just using distributive property. Now you can see that this one must be exactly as this one, and which can be initially, like we said, divide both sides by a. This is nothing but this one. This is always equivalent because a is never 0. Otherwise, it won't be a quadratic equation, it will be a linear equation. Okay, so if that's the case, now you can see why this guy must be this guy. This guy must be this guy. Because if we say the two polynomials are always equivalent, then all their coefficients must be equal to each other for corresponding terms. Okay, so that gives you the intuition that x1 plus x2 equals to negative b over a, and x1 times x2 equals to c over a. Okay, that kind of just not rigorously, but clearly explain why this is always true. The Vieta formula is something like this. Okay, once we have this important relationship, and by the way, this should be in every competition math student's toolbox. You always know the trick the Vieta formula, you may not know what x1 and x2 are. But you do know no matter what values they take, they must meet those two relationships. Okay? So that's a really helpful and powerful tool because in many problems, you are not asked to get the value of x1, x2, but an expression that can be generated by manipulating those two expressions, x1 plus x2 and x1 times x2. Together, they can generate a lot of interesting things. And as we see, all the next three problems are just like that. So what does that mean? Well, meaning that, well, let's just say two numbers, two rules, x1 and x, or just like make it better, p and q, the two rules. By the Vieta formula, what is a p plus q? Let me use blue. P plus q, the sum of two, according to this formula, is negative 63 over 1. So that gives us positive 63. And p times q must be this unknown k. So we don't need to solve p and q, but we do know p and q must meet those two expressions or identity equations. And there are some other constraints on p and q, right? Both p and q are prime. That's a huge deal. Why that's a huge deal? Now we can exercise some really good number theory technique. X plus y equals to 63, which is an odd integer. By the pigeonhole principle, one of them has to be an even number, right? You cannot have both p and q at an odd number because you got the total as an odd number. So one of them must be an even number, p and q. So exactly, if both p and q are integers, it must be one is even, one is odd. Cannot be both even or both odd. Otherwise, the sum will not be an odd number like 63. So we know one of them is an even number and it's prime. That's the big deal. And this fact is so useful in elementary competition math problem. You will have to recognize whenever this pops up. That means that when you find a condition that says that you have an even number and that even number is a prime, you know you found it. What is that? There's only one even number that is prime, and that is 2. All other even numbers must be composite, right? Because it has factor of 2, and it's not 2 itself. Then any non-2 even number must be a composite number rather than a prime number. So we know p or q, one of them, we don't care which one, is equal to 2. This could be q as well. So that means that the other one must be 61, right? Because we have 2, then the other must be 61. Therefore, the product must be 2 times 61, which equals to 122, and that is our k. Done. Okay, this problem is just really a hard test on whether you know the Vieta formula. If you don't know, there's not much hope you can solve it. Okay? But if you do know, this is I wouldn't say piece of cake, but it's definitely the walk in the park. Because look at this. Once you know the Vieta formula, what that gives you just this. And the rest is some basic number theory technique. All right? Okay, we are already over 5 minutes, but we still have some problem. But we spent so much time on Vieta, so the rest should be very straightforward. Okay, so what is some of the reciprocal of the rules of this equation? First of all, whenever we see an equation like this, one has an x, the other has 1 over x looks like it only have a linear term, but it's really quadratic equation in disguise, right? Because we have 1 over x, so we have to multiply both sides by x. When we do that, the linear term becomes a quadratic term. This must come from 2004 math count. Remember, it's x, so we multiply that, it becomes x squared, and the constant term 1 becomes the linear term x, and the original 1 over x becomes 1. So indeed, this is a quadratic equation in disguise. Okay, so we have a quadratic equation, and we are asked to get what? The sum of the reciprocals of the two roots. Let's just say the two roots, p and q. I actually prefer x1, x2. But for those of you who feel uncomfortable with this notation, I can stay with p and q, anything like m and n, a and b, whatever. So let's say the two roots are p and q. P and q are two roots. What do we need to know? The sum of the reciprocal, so that's 1 over p plus 1 over q. And you should really develop some really very fundamental manipulation on simple polynomials or expressions. You should immediately recognize this. What is this? This is nothing but a p plus q over p times q, right? This is just by straightforward the fraction. You get the same denominator p and q, and then the numerator p plus q. Now you see how to do this problem. Use the Vieta formula, because this expression, like we said, is based on two things, p and q and p times q, and they are directly available through the Vieta formula, right? This is what exactly how the Vieta formula can help us. It gives us p plus q directly from the coefficients of the equation and also the product. So the rest is simple. You get those two values by the Vieta formula, then get this, and that is what we need. Okay, so this is also kind of straightforward test whether you know the Vieta formula. And finally, the last problem is the same thing, but with a little bit more algebraic manipulation. All right. So you get a quadratic equation x squared plus m times x plus n equal to 0. So two coefficient, I should say, and one of them is not a true coefficient, it's just constant value. So the coefficient for the linear term x is a unknown m, and the constant is m. Both are unknowns, but they have roots that are twice roots of another quadratic equation, but this time we still have m here, but we introduce one extra p. So now we have three unknowns, m, p, and m, but we know a very nice relationship. The root of the first one is twice the root of the second one. And we also have constraint, they are all non-zero. None of the three coefficients or constant terms are 0. Now you need to evaluate n over p. What is this? So when you see this, you know you need to do some algebraic manipulation, and you can always get there. Since this is a good problem, so confidently manipulate your whatever algebra you will have, and just believe that it will eventually lead you to this term. That's how you approach this. And apparently, we don't know anything. There are too many things. This is an equation with unknown coefficient. How can we solve them? Well, you don't have to. The nice condition is that one set of roots are just doubling the other set of roots. And Vieta formula once again will help. So let's start with this second one, because we say that we want to do the times 2, not times 1/2, because that's the same thing. The roots of the second equation must be 1/2 of the equation of the first one, but we want to stay with the smaller ones first. So we have x squared plus px plus m equals to 0. Let's assume we have two roots here, x1 and x2 that are the roots of this quadratic equation. By the Vieta formula, x1 plus x2 equals to negative p, right? x1 times x2 equals to m. Those two are available, although we don't know what is p or what is m. Let's take a look at the first equation. X squared plus mx plus n equal to 0. By that statement, the solutions of this equation just twice of those two. Therefore, we know 2x1 and the 2x2 are the solutions for this version of the quadratic equation. And once again, by the Vieta formula, we have a pair of relationship that is 2x1 plus 2x2 equals to negative m, right? And the 2x1 times 2x2 equals to n. So what we have by applying the Vieta formula twice on the two quadratic equations, we get a set of 4 identities. That's super nice. And they're not just random, right? You can clearly see the relationship here. So what that means that because this is strongly related to this, and this is strongly related to this, we can immediately translate those two sets of equations into what? Negative m, which is right here, equals to twice of negative p, right? That's the fundamental nature of this fact that the second set of roots twice the first set of roots. And similarly here, now we get 2 times 2, that's 4 times. So n equals to 4 times x1 times x2. So n equals to 4m. Wow, that's something really close. Now you can see that the problem becomes really trivial, right? What do we need to know? We need to know what is n over p. Don't you see the solution already? You just need to plug in this, cancel out the m. So m equals to 2p, right? Because negative m equals to negative p, so m equals to 2p. And you just plug in into this, so n equals to 4 times 2p. There we go, equals to ap. So what is n over p? That's 8. Done. So once again, this is just slightly more complicated application of the Vieta formula. But you should keenly recognize why we are doing this when you see something like the first 2 roots are just exactly twice the second 2 roots. That's a very nice relationship because look at the Vieta formula. x1 plus x2, x1 times x2. If you are told that there's another 2 solutions of another quadratic equation twice of rows, you can immediately recognize that the same Vieta formula can be easily extended for the other one as well, right? Because this is just double up and this is twice multiplied by 2. So 4 times of this. And that's how you use the Vieta formula. So the last 3 problems in today's lecture are all about using the Vieta formula. And you have to understand this very, very well. First, you need to memorize the formula. But the way to memorize it is to understand why this is true. Okay? And we use just the fundamental theorem of algebra to do the manipulation. Also, that was not rigorous, but you can clearly see why x1 plus x2 equals to negative b over a for the quadratic case. Okay, if we have higher degree polynomial, that's the formula will get more general. But you will not be tested on those things. So it's always at most quadratic equation, and those formulas are very helpful. That's it for today. We manipulate a lot of the algebra today, but that's the fun part. I will see you next week. Bye.